Welcome to Lesson 6. We've talked about how we learn math and the strategies you can use in school and life. We're going to think in this lesson about what math really is and see some examples of maths in action. So we talked in the last session about how math is all about finding a general idea. Another way to think about that is that math is really all about finding patterns. And we can think of patterns as these kind of patterns, but we can also think about all of math as being about pattern finding. So when you look at a new area of math, there's always a pattern to see.
Oh, I see the pattern. When we have a right-angled triangle, the squares on the two sides always add up to the square on the hypotenuse.
Think of math class as a time of working out patterns.
Be a pattern seeker.
When we ask many people what math is, they'll say it's about numbers and rules and rules and rules. But when mathematicians are asked, they'll usually say math is about the study of patterns. Keith Devlin is a top mathematician at Stanford who's written many great books, and this is one of them. It's called Mathematics, the Science of Patterns. And as he says in the book, as the science of abstract patterns, there's scarcely any aspect of our lives that is not affected to a greater or lesser extent by mathematics. For abstract patterns are the very essence of thought, of communication, of computation, of society, and of life itself. So you see, Keith defines math as the science of abstract patterns.
Math is a way of making sense of the world, and math is everywhere in the world. If you get in the habit of seeing math in the world and thinking about the patterns you see, it can be really helpful and put you on a great learning path.
Math is a human activity, a social phenomenon, a set of methods used to help illuminate the world, and it exists throughout nature.
One really famous sequence was discovered by someone known as Fibonacci. He found a sequence of numbers so that each number comes from the addition of the two before. The first few numbers in the sequence are 112, 358, 13. Let's have a look at Fibonacci in nature.
We can take Fibonacci's famous sequence of numbers and make a spiral with them. So 1, 1, 2, 3, 5, 8, 13. Since the sequence starts with 1, let's also start out with 1, so draw a square with a side length of 1. Since the next number is also 1 in the sequence, let's add another square with a side length of 1. The next number in the sequence is 2, so let's draw another square with a side length of 2. You can probably guess the next square in the sequence. Now let's add the next square with a side length of 5. And if we do this several more times, we get 8, 13, 21. Look at this cool spiral. What's so cool about this spiral is that it's found in all kinds of unexpected places around the world. Like in a seashell, the Mona Lisa, or even Darth Vader's mask. There are other links between Fibonacci's sequence and spirals. Let's take a look at this pinecone, which has spirals similar to the ones you saw in the previous example. We can draw each of the spirals that we see. Count the number of spirals as we draw below. The number of clockwise spirals is 8. And there are 13 counterclockwise spirals. Do the number 8 and 13 sound familiar? They're part of the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13. Fibonacci spirals occur all through nature. How cool is that? Write in your own words, what did Fibonacci discover?
We saw lots of examples of Fibonacci in nature. But that's not the only math in nature. If we think about snowflakes for a minute, we see something amazing. Snowflakes are beautiful and all unique in their own way, but they are also unified by a single pattern. If we look closely, you'll notice that all snowflakes follow the general shape of a hexagon. So snowflakes almost always have 6 points. Why, you might ask? Well, if we take a closer look and zoom into the water molecules that make up the snowflakes, we see that water freezes in the pattern of repeating hexagons. This shows us some of the beauty and art in mathematics.
We've seen a lot of math in nature, but what's really cool is that we can also see that animals use math all the time. Remember we talked about the importance of intuition and how math should be intuitive for you? Well, math is totally intuitive for animals. Let's have a look at this spider.
Spiders are experts in spirals. When a spider makes an orb web like the one we see here, it first creates a star shape between 2 sturdy vertical supports. Then the spider begins to make a spiral. It needs to make this spiral as quickly as possible to strengthen the star, so the spider chooses to make a logarithmic spiral. In logarithmic spirals, the distances between each successive turn around the center grow by the same factor every time. This means that the spiral expands outwards more and more quickly the larger it gets, perfect for a spider in a hurry. But this logarithmic spiral leaves lots of spaces in the web, so the spider starts a second, denser spiral. This new spiral is an arithmetic spiral, which means that the distance between each turn of the spiral is the same. This second spiral takes the spider much longer to make because it has to take many more trips around the center of the star, but it will surely help the spider catch many more insects because it eliminates large spaces from the web. This amazing feat of engineering could be constructed using lots of cool calculations, but the spider intuitively uses math to create and follow a simple, elegant algorithm.
Which of these animals do you think is also an expert in building spirals? If you chose snails, you're correct. Snails grow shells that follow a logarithmic pattern. Another animal that uses math intuitively is a dolphin. Dolphins, like spiders, use math in amazing ways. They actually find each other in water by making clicking sounds, and then as the sound waves travel, they hit the other dolphin and rebound back. And the first dolphin uses the length of time it takes for the sound to come back, as well as the quality of the sound, to work out where their buddies are. Did you know dolphins could calculate with distance and time? If they could also speak human, they could be your algebra teachers. Animals use math intuitively all the time, and so do sports players. Have a look at another of my students now who's an expert tennis player. What math do you think Caroline is using intuitively as she makes this forehand cross-court shot, a forehand down the line shot, and a backhand shot?
You probably noticed that the angles Caroline chose were really important for the shot she made. She was intuitively using other math too, such as distance and time. If you play or watch soccer, you will know that soccer is also about angles. When a goalie positions herself or himself, she cuts down the scoring possibilities by limiting the angles available to a striker. Having a good sense of angles is really important to being a good goalie.
So we've looked at math in tennis and soccer. I also have 2 students who are amazing dancers that we're going to see now. So first we're going to watch KK and Erica perform a partnering dance sequence and think about the maths involved. Now let's see some of the math inside the dance. Now it's your turn to think about the math. We have a couple of short clips for you to watch, and first we're going to watch Erica performing some ballet. After the video, you'll be asked a question. We see lots of math in that clip. Maths of patterns, balance, and angles, for example. Let's think about the angles for a minute. Which angles did you see in the ballet moves? Now we're going to show you KK's feet as he performs a hip-hop dance. And again, after the video, you'll be asked a question. We see lots of math in that clip. Math of patterns and beat and balance and angles. Which pattern do you think you saw in the hip-hop video? We have one more sport to show you from yet another amazing student who, as with the tennis players and the dancers, worked really hard to learn this, using growth mindset thinking that we also need in math. This time it's Alex, who's a juggler, and he's going to explain the math of juggling to you, which is all about patterns.
So juggling one ball would just mean passing one ball from hand to hand. And so that's what we're going to call a 1. So then I can use that in patterns and say this pattern, which is called 7-7-1. But you can see the 7s are high, and then there's a 1, which is a pass between the hands at the bottom. The way Sight-Swap works is that for each different number of balls, we say that one throw in that pattern represents, say, with 5 balls, a 5, or with 4 balls, a 4. And then each throw in the pattern, the height of it, is determined by what number we use. So, for example, I might do 5-3-4. And you can see that the 5 in the middle is the high throw, which is in like a ball in a 5-ball pattern. The 3 is the really small crossing one, like a ball in a 3-ball pattern, and the 4 goes out on the side. And now using that, we can make tons of more complicated patterns. So like the 6-ball version of that one is 7-5-6. Well, the 7 is in the middle, the 6s are on the side, and the 5 is low in the middle. Now, we also might want to know which patterns are going to work if we just write down a random string of numbers, and which ones aren't. And we can do that by seeing if the average of those numbers is the same as the number of balls. So you'll notice with 5-3-4, if you add all those numbers up, you get 12, divide by 3, and you get 4, which is the number of balls we're using. And if you try that with 7-5-6 or all these other patterns which work to juggle, as in the balls don't collide and they don't land two at once in my hand, all of those averages will be the same as the number of balls.
We hope you found that interesting and cool to watch. Now, a question. What math is involved in juggling? We've seen a few examples of math in the world, in sport, in nature, and in the animal world. Students often think of math as a dead subject invented years ago, but it's a living, breathing subject that's all around us and that we need to make sense of the world. And math is changing all the time with new ideas, new questions, and new methods being put forward. We're now going to think about the ways of mathematical thinking that are needed for success in the world. What other cool examples can you think of examples of math in the world?
Work is becoming more and more mathematical. As we move onwards into our technological age, businesses are increasingly having huge amounts of data, and making sense of the data is a key role for employees. This means that they need to be able to ask good questions, work out a pathway through data, talk about their pathways with others, and represent their work in lots of ways, like through pictures, graphs, and words.
What employees don't need is people who calculate fast. Calculations are done by calculators and computers. What is needed is people who can be creative with math, work as a team, and problem solve.
In the last session, we met Sebastian Thrun. Sebastian, as you may remember, is a vice president of Google and head of Udacity.
As Sebastian heads up teams of people using math all the time in Silicon Valley, home to many of the world's leading technological companies, such as Facebook, Google, Yahoo, Apple, we asked him what math was needed in the world, and he said this.
For many kids, math provokes an allergic reaction. Yet it is perhaps the single most important skill to have if you want to find a job in Silicon Valley. To me, math is all about problem solving, reasoning, using intuition, and making connections. It's not about memorizing formulas.
He said something else really important too.
The world is mathematical. I am excited to see so much innovation in the teaching of math. I believe every student deserves to be a math hero, and I believe every student has the potential.
The top users of math, employees at the world's top companies, use math very creatively to design, to solve problems, and to create.
Here are some of my students engaging in math in the ways they probably will when they graduate from Stanford. In this clip, they're involved in some design work, designing a new room layout, a wallet, and a backpack. You may notice in the video that the students are engaging in math by posing a question, modeling a situation, both using drawings and real objects, representing their ideas with drawings and charts and words. They're working collaboratively, sharing mathematical ideas and building on each other's thinking. Most companies want people working in teams, and they want them talking through mathematical pathways, being able to say why they chose methods and how they connect to each other. Which of these statements do you agree with? You can choose more than one. There's another piece of information I wanted to leave you with that's really important. There are lots and lots of apps and games out there that are claiming to help you with math. But a lot of them just offer practice of calculations, and they often encourage you to work at very high speed, which we know can be damaging for people. I'm a big supporter of math apps and video games that are good, that offer math as an interesting subject that's not just about calculating. Math apps and games can help you practice, and if they're good, they'll also help you understand some key ideas. It's also really useful just to play and explore with math. So I've chosen 3 apps and a video game to show you here to give you some ideas of what's useful in a math app or a game. So the first one we're going to look at is Was It Trouble? I like this app as it's one that develops understanding of important mathematics, adding, subtracting, factors and multiples, at the same time as developing number flexibility, which we've learned is super important. The aim of the game is to free the little creature from jail by turning the cog to release the key. Then you get to use the same math to solve really challenging puzzles, which will help develop those brain muscles. The next one we're going to look at is Motion Math. I chose this app because it also helps develop understanding of important mathematics, particularly number and fractions, and it does it visually. We've learned how important it is to learn math through visual representations, and this app helps you really see the mathematical ideas. So the third one we're going to look at is called DragonBox. This app teaches you algebra by requiring that you cancel and move objects so that one is left alone. And by doing this, you're actually solving for x and having fun at the same time. It uses different visuals and teaches you how to balance equations with lots of useful algebraic thinking. And the final one we're going to look at is called Math Breakers. This is a 3D game that does something really valuable. It lets you play with math. It lets you act on numbers by, for example, cutting them in half with a sword or feeding them into machines. And it teaches number sense conceptually in an engaging open environment that lets you play with math. So now a question for you. What makes a good math game or app? As it's the last part of the last lesson, we want to show you some of the big ideas of the course and get you to really reflect and think about them.
So, how did y'all feel about the class?
I thought the class was great. The part about growth mindset really stuck with me. When I saw that the soccer player had a growth mindset and she played really well when she did, I knew that if I had a growth mindset in math, I could also do math really well.
Yeah.
What about you?
I don't know. I think the part that really stuck with me was being able to talk about math out loud and studying in groups. And for me, it was real reflective of my experience here in school. Once I started working with study groups and studying with other people and talking about the problems, I was able to like really understand it, and I could perform a lot better in class. I guess it was really cool, like looking at the theory behind that. Yeah. What about you?
Well, like, to me, when we talked about speed was really cool because I always felt pressure to be like faster, to be better at math or something, and learning that those are like not even related was really cool. Like that mathematicians can be slow and everything.
Did you ever have those like speed tests in elementary school?
Yeah.
I did. I used to hate making mistakes on that, and then I learned that making mistakes is good and that your brain grows when you make mistakes, and so that was really interesting. I wish I'd known that back then when I was taking the speed test.
Yeah.
Do you guys remember that part of the lesson where we saw the blue aisles and the pink aisles?
Yeah. I mean, I hate stereotypes. Like, I really don't like that just because I love poetry, people think that I can't like math.
Yeah, I absolutely hate it when people just, for some reason, assume I can't do math. I love math.
You've heard some of the things the students thought were important for them. Now we'd like to hear from you. First, can you just pick from this list the most important ideas for you?